All right, good morning. So let's take a look at what you should really pay attention to in addition to the lecture. So your assignment number 3 is going to be due soon, okay? Let's remind you about the deadline for submission. So if you look at the instruction PDF, it will be due 12 noon tomorrow, all right? You should really try your best to really finish the assignment and struggle through it and discuss with me or the TA if you got any trouble, right? We got all the resources available to you. You just have to reach out. And after the submission deadline tomorrow, I'll also give you the solution. You can go through them, but I think since your programming test 2 is also coming, and that's directly relevant to your assignment number 3, just by looking at the solution itself would not be sufficient, as you know. You got to really practice. So I would say take a look at the solution. That'll be the first step only, and then you got to practice. And then trouble, reach out to either the TA or myself. And as I mentioned earlier, much earlier before, how do you reach out to the TA? They don't really have any in-person office hour. You just have to email them. So we got 3 TAs over there, over here, right? That's what I mentioned before. You just got to reach out. Otherwise, you're more than welcome to come to my office hour. We can go over even your programming test 1 submission if you want to go over the solution. More than happy to do it. Okay. So that's about assignment number 3. And for your programming test number 2, and the guide, I released that just yesterday, and also the practice question. I gave you 2 questions there. I think they are not trivial, but I think they're not that hard either. So I think you should really at least finish them, and then you can easily go to the interview website. You can easily Google yourself for more practice questions. Right? There are many example questions out there. But in the actual test, pretty much like your programming test 1, you will be given 2 questions. So question 1 and question 2. And both of them will be related to trees. And they will be not like a question just for recursion. But as I said before, if you want to program a task on trees, unavoidably, you most likely have to use recursion. You just embed it. Okay? So you'll be given 2 questions, and you'll be still given 1 hour, like last time. Okay? And then, just don't forget, we also released the makeup lecture for your past written test number 2. And that one is about the merge sort and quick sort. I think that's a very informative lecture to show you how to do the algorithm and also how to derive their running time. Question? Yes?
Yeah, the programming test, is it going to have along the tree sequence, like this too, like the assignment?
Oh, it's going to be like the assignment, yes. So let me be more, let me be very precise. So the question was, what's going to be the given stuff you have to assume for programming test 2? So if you, for example, go into the starter code of your programming for your assignment number 3, you can see under the tests package, you were given SLL node, right? That's something you program with for your assignment number 2 and programming test 1. That one will be given, and also the tree node, right? And again, for the tree node, I also mentioned some resources which we gave to you in the assignment instruction and also in the starter test, which is this one here. Test general tree. We'll give you this test to you as well, just in case you want some reminder during the test. But your best advice would be to get yourself very familiar about the basic manipulation of the tree node and the SLL node in this test class. You don't want to waste too much time just brushing up during the test. Right? So these will be the stuff you will be given in the programming test. Okay? I hope that answered your question. Okay. Guys, any other question about anything about the course? Okay, why don't we do one more glance of the course calendar, and then we can move on to the exciting stuff for today. Okay, so if you look at the semester calendar, we're still on schedule. We are now over here on the 27th. So next Monday, this time, we'll have your final programming test. And then, of course, later on, we're also going to have your exam. I think that would be to your guys' advantage because the exam is on the 23rd of April. I think I'll reach out to you guys maybe a little bit later, maybe after the study day. After this day, we can maybe schedule some review session for you. You can come over in person and ask me questions, right? We can do that too. All right, so that's about programming test number 2 happening next week. We got today, we got Wednesday, and we got next Wednesday. That'll be the last class for the semester. And then to really make up for the time over here, I'll give you guys something. So whatever we cannot really finish on the heap data structure. Hopefully not too much. I will assign them to you for the makeup lecture. That for sure, it will be less than 90 minutes, roughly. Right, so that's kind of the plan. And for your assignment number 4, that one there, I'll release that maybe around Wednesday time. So that one will be a final practice for you. I think that one there is also going to be some tree exercise, which will be definitely worth doing. And then make sure you also submit it before the submission deadline to get the credits. Yes, question? We are not learning hash table for this course, but I'm definitely going to learn about heaps. If I really have to choose one, I think since we got limited time, I'll choose the heaps data structure. Hash table, I understand, is a very common data structure, but you can also easily pick up the idea yourself beyond the course. But for the heap, it may not be so easy. It does have some mathematical construct. You really have to maybe have some guidance to begin with. So that's why I decided. All right, guys, any more questions before I move on to binary search tree for today? Okay, awesome. Well, we still got about 2 weeks for the semester. And once we get to the exam period, I know everybody will be busy. I'll try to make myself available, but if you really want to reach out to me in person, this week and next week will be the best time. Okay? I'm not saying it's impossible to reach me in the exam period, but you'll be busy as well. Okay, let's now talk about binary search tree. And don't think about this topic being too difficult. One thing about binary search tree is, number one, it's a binary tree, for sure. We know about what a binary tree is. What you have to pay attention to is something we're going to talk about in just one moment called search property. We gave you some very rough intuition last time, but it's not complete. So we're going to talk about search property right away. So once we learn about, so this is a one-line summary you have to remember when you later on review this topic for the exam. Think about binary search trees is a special kind of binary tree which specifies on search property. Okay? And later on, maybe on Wednesday or next Wednesday, we're going to learn about another thing called balanced binary search tree. We're going to add another property to satisfy, but that's for next week. For today, just remember the number one take-home message will be what a search property is, which is not difficult to define. Let's get on with that. Okay. Okay, and binary search tree can also be defined recursively. Let's go over some bullet point, and then we'll do illustration. Okay. So this is the idea. Each internal node in the tree, right? Each node that has some child nodes, at least one, either 1 or 2, was 0. Sorry, either 1 node or 2 nodes, since we talk about binary tree. Otherwise, if you got 0 node as child, that means it's external. And every internal node is going to store an entry. And here, this entry here is a very special term. Whenever we talk about entry, it's not just a single value. Usually, it's about 2 values. It's going to be a key value pair. Okay, I'll show you what I really meant. Okay, so whenever you talk about a node in the binary search tree, we talk about something called entry. Okay, let's understand what an entry is. For our purpose, the entry has 2 parts. Okay, entry. That means every node should really store 2 things as the entry. Number 1 is the key. Okay, so this will be for searching purpose. So some of you, I forgot who, bear with me. So some of you asked me about whether or not the search key over here can have duplicate. For example, if you got 32 here, you also got 32 here. The answer is no, you cannot. You cannot have duplicate. Okay, I'll talk a little bit more about it later. And another part of the entry is called value. You can think about the value here is more like elements. You know, the singly linked list, every node stores an element. Also for the tree node, every node stores an element, like a data. Okay, so this is like a data element. Okay, so there are 2 parts. And for most of our purposes, we talk about, you know, searching, insertion, deletion, different operation on the binary search tree. We only visualize the search key over here because all those operations will depend on how the search keys are distributed, not the data element. Data elements are simply just associated with the corresponding key. So typically speaking, we don't really include the data element just to simplify the diagram. Okay? So if you take a look at, for example, here, this value here, it is the search key. which is only part of the entry, right? Whereas the elements is just omitted. Elements omitted. All right, so hopefully that's not too bad, right? All right, let's now move on. We'll talk about entry. And then each node in the left subtree of P should be such that the key must be strictly smaller. Symmetrically, each node in the right subtree of the internal P, it should be strictly larger than. That's kind of what you guys observed last time. But let's now revisit again. So what we are saying is, if you're considering this particular node, and let's call this node P, okay? And then we have two subtree. Think about this guy over here is the left subtree. Left subtree of P. And this guy here is the right subtree. Let me just make maybe use a slightly different color. How about this one here? And this one over here is the right subtree of this particular node P. And the search property tells you, given any node, you have to make sure the subtree rooted at that particular node will satisfy the search property, which is defined as every node in the left subtree of P, they must be strictly smaller than for their key values. Only the key values, not the data value. Whenever we talk about search property, we don't really care about the data element value. Okay? So here, and I know you guys learned about universal quantification back in 1090, right? So maybe write a little bit of math over here, a little bit, that can make it a little bit more precise. So what you have to remember is, for every node, is simply elements of the left subtree of P, and P is over here, the root. It is the case. The key of N should be strictly less than the key of P. All right, that's kind of the universal quantification you guys learned in 1090. Okay, if you're struggling with it, let me know. Otherwise, you'll assume you know kind of the basic, okay, over here. Symmetrically, every node in the right subtree, it should be such that the key value, rather than less than, should be greater than. Okay? Let's write it down just to be complete. And then I'll just do one more example. Okay, so for every n in the right subtree of the root over here, it is the case that the key of any n over here should be strictly larger than the key of P. All right? This property here should be applied to every subtree. Right? Remember, one of the questions in the written test was how many subtrees are there in a given tree? You simply calculate how many nodes there are in the tree, right? So you have to make sure this search property is applicable to every node in the tree. Let's now talk a little bit more here. And there's one more slide I want to show to you, because some of you also asked me about what these really mean, the squares. Okay, they have some special meaning, which I mentioned last time. They are simply external nodes. Okay, I'll show it to you, and I'll come back to that example. All right, there's a diagram which is we're working with, and in the case of binary search tree, and also later when we talk about balanced binary search tree, we're going to have the following convention, which will be reflected in your Java implementation as well. So we store the entry only in the internal nodes. For external nodes, we don't store anything useful. And this strategy has been used in the doubly linked node. If you remember in the doubly linked list lecture, we talk about introducing header and trailer. They don't store anything useful for data. They are simply there to simplify the logic of the code. And the external nodes over here for binary search tree will serve the same purpose, as we'll see. Okay, just remember that remark. Okay, let's take a look. Yeah, so I talk about header and trailer in DLL. They're kind of the connection you want to make. And now for here, external nodes will be sentinels, like a guarding nodes. They will be there just to simplify the coding logic. They wouldn't really improve the running time. Running time will remain the same, either with or without this particular structure, but they're going to simplify the coding logic, as we'll see. Okay, so that's one diagram here, and this one here simply is here. Okay, let's take a look. Let me finish something, and I'll get to you. Give me one moment. So if you can take a look at the external nodes are over here, the one I'm highlighting in pink. These are the external nodes. They are simply the nodes that do not have any further child nodes. Okay, the pink ones. On the other hand, the green ones are those nodes that has at least one child nodes. The green ones are the internal. So this will be the diagram you saw on the slides. You just have to know, first of all, the distinction. Let me say one more thing, and I'll get to you. Okay. You have to make sure this will be the simplest case. Simplest case of a binary search tree. Okay, over here. So now, since we said the search property that we talk about, again, the search property is defined as just this. That's a search property, right? If I ask you to really state the search property for a binary search tree, that's what you have to answer. Okay? Now, what would be the smallest subtree that can actually satisfy this particular search property? Apparently, external node over here can satisfy it because itself contains no data and also no key. In that case, you have no possibility of violating the search property. So that's why it's the simplest case by default. Okay? Because there's no key violation there. So it's like a base case. Okay, we'll see that also when we get to the actual method. Now, if I circle this particular one, in order for this to really satisfy the search property, you can see here, this is the root. And then we have over here, this part over here is the left subtree. And this part over here, right, is the right subtree. In order for the subtree rooted at this particular node to be a binary search tree, it must be that this is a binary search tree. And this is also a binary search tree. And also, every node has its key value over here strictly less than the key for the root. And symmetrically, the key values for every node in this right subtree must be strictly larger than the key for the root. Let's double check. If you take a look at that, every node over here has their key value strictly less than 44. And symmetrically, every node over here has its key value over here also strictly larger than 44. Okay? And let me give you guys some counter example, and then we're done with the basic definition. Of course, when I do this, it will be quite obvious about what the change is. You can easily tell the justification. But in the actual exam, I might just give you some tree to begin with right away and ask you to really prove or disprove that being a binary search tree. Okay, for now, let's just do something very easy. Let me give you two examples. How about this? Let's say this one and this one. Okay. Let's say for this one here, I'm going to change this one to be 69. And for this one here, I'm going to change that to be, give you one moment. It would be, how about 83. Let's say this is question number 1. Question number 2. The question is the resulting tree still a binary search tree? All right? And to really judge it, you have to check the search property on every subtree, basically. But now we can do a little bit shortcut. Since I only modify this, and only modify this, you can look at maybe just a subtree that's being impacted. That might be a little bit easier for you. Okay? I'll give you guys just 1 minute to think about, right? I want to know for question 1, yes or no, is it still binary search tree? And for question 2, yes or no, is it still binary search tree? You know, just before I get to the answer, you have some question, right?
When you said that the external was Sentinel?
Sentinel. So Sentinel, okay, before I ask you guys the answer. So these nodes are called the Sentinels. So that means they themselves don't really store any useful data. They simply occupies very minimal storage over there, like a header and trailer for doubly linked list. So the reason we have those nodes is because when you look at the actual code, which I will show to you, you can easily actually return sometimes the Sentinel nodes, and that will simplify the logic for the coding. That's something we'll see. That's what I meant by Sentinel nodes. They don't really store any useful data, but they are there so that you can actually, you would be required to program less or fewer edge cases for your code. Okay? Correct. So every value here will be just part of the entry. We don't really, put two values there in each node. That would be a little bit confusing. So that's why we'll only put the key values over here. All right. So let's now talk about, how about for number 1? Is it still a binary search tree? Yes? Okay, good. Okay, so without bothering you, how do we justify it? Okay. Later on, we're going to see the easiest way to justify will be just do an in-order traversal of the tree and make sure the resulting sequence will still be sorted. So this will be a sorting property I'll talk about on a separate page, but just for now. Okay? You can see here, for example, if you look at this particular subtree, 65, and then this will be, this will be the left subtree, and this part here will be the right subtree. You can see 54 less than this. Good. 69, 82, 80, strictly larger than that. So this part is okay. But let's check more. If you look at, let's say, this particular subtree. So you have the left subtree over here. Right? That one there is also good because that one there, 69, 80, strictly smaller than 80, 82. Right? And final check, what about this node itself? 69, you only got the right subtree. In that case, 80 is strictly larger than 69. That's kind of the iterative process you have to do to check for every node and make sure every node, its corresponding subtree should be a binary search tree. All right, so the first one here, yes, still a binary search tree. What about the second one? Is it a binary search tree still? Okay, so if you said no, good sign. Why? Exactly. So here, easily, you can easily justify that. Let's say if I look at this particular tree, that's the root. And this one over here is a right subtree. So this is not a binary search tree because 82 in 83's right subtree is not greater than it. Right? If it, for that to be a binary search tree, this value here must be larger than that, but it's not the case. Okay? Yeah, not too bad. So you just make sure you pick up the search property. That's really important. So binary search tree, again, nothing complicated. It's a binary tree plus search property. Okay. Okay, let's now move on to the next page, next topic. And we talk about it. Yeah, if you're still confused about being sentinels, we'll see very soon today. Okay, sorting property. So this is more like a logical consequence of search property and some traversal. Okay. Let me just tell you the result directly. And in order traversal of a binary search tree, assuming that it satisfies the property, of course, the search property, is going to give to you a sequence of nodes whose keys are arranged in an ascending order, from smallest to largest. Okay? And let's see why. There will be some justification on the slides. We're going to see that. But let's now take a look at one example here. Given this particular binary search tree, okay? And let's now try to do some in-order traversal, okay? So this is the root over here. And then, if you guys remember, in order to do in-order traversal, the tree must be a binary one. And also, you have to make sure you traverse recursively the left subtree first, and then the root, and then recursively traverse the right subtree, right? That's a principle we talked about last time, okay? So let's now do in-order traversal. In-order traversal. Okay, let's now try that. So we're going to traverse the left subtree first. So that one there is going to be something here. So this will be the in-order traversal of the root, 44's left subtree. And then we're going to do 44 afterwards. And then we're going to do, over here, this will be the in-order traversal for its right subtree, right? In-order traversal of 44's right subtree. Okay? All right, so guys, we did some exercise last time. For now, I'm not going to trouble you. I'm just going to write out the answer directly. But if you got trouble understanding in-order traversal, reach out. Okay, what should be the in-order traversal? It should be 8, right? And then 17, and then 21, 28, and then 29, and then 32. And I don't put any contents about the external nodes. For example, here, you can see when I just do 8 directly, I don't really put any key value in the external node because they don't store any key value. All right? That's about the left subtree result. What about the right subtree? Okay, so I'll start with 54, and then 65, 76, and then, of course, make sure I do this one here, 80, and then 82. Sorry, I'm running out of space. I'll put it here. 88, and then 93, and then 97. Okay, so that's a sequence. But don't worry, on the exam, you will get enough space to write down your answer. Okay. Okay, so what can we observe over here? Number one, given that the tree is a binary search tree, given a tree that is a binary search tree, number one, we know that the search property is satisfied. Number two, in order traversal. It's a recursive procedure, right? It can be applied to arbitrarily complicated binary search tree. Okay? In that way, we know that we always traverse the left subtree first, and then the root, and then we traverse the right subtree. Left subtree, followed by the root, followed by the right subtree. So these are the two things we are given, basically. And that one tells you the result is a sorted sequence, like this. Right? You can see here, 8, 17, 21, all the way to over here. Okay? That's a sorting property. So it's, as I said, it's not very surprising as long as you're given a binary search tree. doing an in-order traversal guarantee is going to give you a sorted sequence by the keys. Okay? All right, guys, any question about this? Ferrets. Yes. Yes, that's correct. So in the exam, there are different possibilities. For example, let me just give you guys some tips. So if I simply just give you some tree to begin with, I simply ask you, is it a binary search tree? Based on the sorting property, you can simply just do an in-order traversal of the tree. In that way, why don't we do that very quickly? Okay? Let's say just for this part. Okay, that will illustrate the point. For this part here, if you do in-order traversal, that one is going to be 54, and then 83, and then 70, and then 76, and then 82, and then 80. Apparently, you can see this part here is not sorted. So this one tells you the tree cannot be binary search tree because it does not satisfy the sorting property. Okay? Yeah, that's one possibility. Or number two, I can simply say, okay, now describe the sorting property of a binary search tree. In that case, you can refer to the slides. So that means by doing an in-order traversal on the binary search tree, you're going to get a sorted sequence according to their keys. And how do you justify it? And I already talked about it. You have to talk about the nature of the in-order traversal and then the search property of the binary search tree. If you combine these two things, these two principles together, you're going to get a sorting property. Okay? So Varus, I hope that answered your question. Okay? Right? Quite a bit of details to really remember. I think it's not too bad, right? You just have to remember how to do in-order traversal, how to define the search property recursively, and the sorting property will just be consequential. Okay. All right, any question? Yes? Yes.
But for the searching property, when we go from our higher node coming down to our left node, which are smaller and smaller, but for the left nodes, they sometimes have a right node that's larger than it. How do we discern then the searching property?
Okay, very good. Okay. Let's say this. I think that might also be clarified much further once we talk about how you can do binary search tree on how we can do a binary search on a binary search tree. We'll talk about how you can do binary search on a linear array that's already sorted. Remember? That's one of the makeup lecture for your written test too. And let me just talk briefly, and then hopefully that will clarify even further. Okay, you can feel free to ask me follow up. Let me just go back here. This will be a little bit of rehearsal about how we do binary search tree, binary search. Let's say, for example, let's say I want to search for 28. Okay? Now, the assumption you can make is in order for you to do the search, the input tree is a binary search tree. That's something you can assume. Now, let's say I'm now here. Apparently, this is a starting point. 44 is not exactly 28. So I know I'm not terminating the search process just yet. But now where should I go? If I didn't tell you this is a binary search tree, you have to go both ways to see whether you can find the elements or the key, because there's no search property. But now, if I do have the search property, should I go to the left or go to the right, and why? So guys, let me rephrase the question again, okay? This is really important. You're given a binary search tree satisfying the search property, and you now want to search for the key value 28. I know that 28 is not really matching the 44. So I should really go either this way to look for the left subtree, or I should go this way to go for the right subtree, or both. Right? It's a very important decision I have to make. All right? Any insight to this? Should I go to the left or go to the right, or both? Yeah, that's good. Spot on. Okay. Maybe that's what you think too, right? Okay. Okay. So the answer is, I know that, oh, sorry. I know that what I want to search for is 28. 28 is strictly less than 44. According to the search property, all the values that would be strictly less than the key of the root must be in the left subtree, if it exists. So the only hope I have is to go to the left subtree, and I know all the elements there will be strictly less than 44. So I can go there and search for that. Okay? Because all the keys in left subtree is strictly less than 44. I can safely disregard this branch because all the values over here will be strictly larger than 44. So that's why the search property here is really important. Okay? All right, guys, I will talk about this a little bit more with some more example. But for now, it's just a little bit look ahead. Somehow maybe helps a little bit? Okay. Okay, so that's about the searching and sorting property. And I would suggest we go a little bit further, and then we'll take a short break. Okay. Let's talk a little bit about how we can implement a binary search tree or binary tree in Java. And let me be clear, the implementation that we're going to talk about right now, they will not be relevant to your programming test too, even though they might help algorithmically about how you do recursion. So for the actual programming test 2 that's going to happen next Monday, you will not be given like a binary search tree node, not really. What you will be given is like what I said in the beginning, just the tree node that you did for your assignment number 3 and the practice test. But in the actual exam, you might be given this to actually do some, write some fragment of code, just for the exam. So you still have time to digest the material. Okay, why don't we do, let me see, this one here. Okay, let's do one, just one page, and then we can take a short break. Let's talk about how we can implement a binary search tree. The basic units for the tree is a node, like what we did earlier. Let's go over this particular fragment of code, which is not very complicated. Okay, we're going to go over that. Okay, so this part over here contains all the attributes. Okay, so these are the attributes. And at the same time, I would like to also compare the structure to a doubly linked node. So we can see very clearly again what's really nonlinear versus linear data structure. Again, that's really important. Let's take a look at this one first. And how do we visualize it? So let's say if I have some BST node. Okay, I might, you can see it's generic over here. I might instantiate it into maybe a string. For example, let's say n. That's my decoration. So I have n here is pointing to some BST node. At the runtime, it's going to contain several parts that you have to be aware of. Okay, let me just draw it that way. Okay, let's do one by one. The first part will be the parent. Right? The parents might point to some other nodes if it's not a root. Right? That makes sense. It's like a general tree. And also we got the key and the value. So here we got the key. And also we got the value. And key over here, typically integer. Typically. Okay, and then for value over here, this will be the elements. All right, so far we talked about 1, 2, and 3. So that's the parents, key, and the value. And what about the child nodes? In your assignment number 3, this will be a little bit different. In the binary search tree case, it's a little bit simplified. You got either the left or the right child. But in your assignment number 3, you actually got a singly linked node, a chain of singly linked node. Each one of them will store a tree node. Right? That's what you did in the assignment number 3. And here we're going to have the left and also the right. That's a basic structure. Okay? And we'll see how to construct a simple tree in just a moment. Are we okay with this? Good. And based on this, how do we tell right away any tree that's going to be built from this is going to be nonlinear? How do we tell right away? Yeah, because they're branching out. Exactly. So guys, the key word to distinguish between nonlinear and linear is about branching. For linear structure, like a singly linked list, you don't have any branching. But for tree, like here, you do have branching. Okay? Oh, very good. So think about this part over here is the branching. That would make it nonlinear. All right, and a very quick brush up for you. How do we visualize each doubly linked node? It would be, let's say, if I got some node of type doubly linked node, it's going to be something like this, right? And of course, you got a previous, this will be the previous, and this will be the next, right? However, it shouldn't really consider this and this being branching, not really. Because this one is going to be the successor, which is unique. On the other hand, when you actually try to branch out, you're just going to the child nodes at the same level. So they're different concept. Okay? So for example, the next over here, you can think about, this will give you the unique successor. And this one over here will be the unique predecessor. Predecessor. And again, let's emphasize, if you got a left and right over here, non-unique child nodes. Okay, so that's why this guy here is no branching. That means it is linear. Okay, we're good? About nonlinear versus linear. Just another reinforcement. Right, we have these four attributes. Let's look at the methods very quickly. So we have the constructor, which is going to initialize everything to default value. That means everything will just store now to begin with. Okay? And we got BST node, which will be the constructor. In the case of the external nodes, you can think about this one over here is the constructor for creating external nodes, storing no key and no value, just null. This will be for creating external nodes. On the other hand, this one here, you can see we give some key and value. And this will be for creating internal nodes. Of course, you might be wondering, what if I just pass 0 and also null over here? Wouldn't that also allow me to create external nodes? Indeed, yes. But just for our convenience, whenever you want to create external nodes, you just don't pass any argument value, just for simplicity. Okay? And we have some Boolean query over here to know whether or not the node is external. You simply check to see whether left and right are simply null. Okay? Think about this. If you got external node, to visualize it, is going to be something like this. Okay, the square. In that case, the left and the right will both be just null. Okay, that's the external node. What about internal node? Well, by definition, if it's not external, it should be internal. But how do you visualize it? Something like this. Internal node. You might have something like this. Of course, over there, you have some key and value pair, right? But normally, we just visualize the key, as we said before. And that one there is going to have some left and also some right. The left and the right. And they are not null, okay? In the extreme case, it could be that you got another internal node over here and maybe arbitrarily complicated in that particular branch. Or you might just have just one external node over here. That one there is also not null, right? Okay, so both of these not equal to. No. Right? And other methods are just accessor. You can get a key and mutator, set a key. You can get a value and set a value. You can get a parent, set a parent. Get left, get right, and also set left and set right. They are very straightforward methods to define. All right, question?
In your specific Java implementation, is there any mechanisms to enforce such a property? Because the way I see it,
Yes. It's a very good question. The binary search tree node here, the class itself does not contain any logic about the tree being satisfying the search property. So for you being a programmer or being a user, if you're given some BST node, in that case, you just have to check the search property yourself. Okay? That itself doesn't really do it. That'll be a little bit more complicated than necessary. So maybe you'll be more precise rather than calling that BST node. I can just call it BT node, binary tree node. That might be a little bit more accurate, but that's okay. Yeah. All right, guys, let me repeat the point. The class definition over here is as simple as that, but itself does not really force the search property for any tree that you can build from there, depending on how you set the parents and set the child nodes. So if you really want to make sure, given some BST node, that's going to be some branching structure over here, whether this is actually a BST or not, you have to check by yourself. Okay? Hopefully that's clear to you. Okay. Why don't we take a very short break, and then we can take a look at some examples about using this tree node. Okay, why don't we take a short break? And we'll take attendance. Okay, if you can get your iClicker ready, and then we can do it quick. Okay, if you can just check in. Okay. Yeah, we're checking attendance now, so please do it. And then if you got trouble, you can just come forward. Okay, everybody's good? Okay. Not yet. Okay. If you're not good yet, okay. Should I close it? All right. All right, sounds good. Now, guys, please take a 2 minutes break, and then I'll come back. Yes. Yes. How about after the lecture? So give us more time. Okay. Yes.
each node has one group predecessor, but it has multiple successors because it keeps branching.
Yeah, you can think that way. That's okay. Yeah.
Thinking like the opposite wouldn't exist, right?
Like
Multiple predecessors, because that would kind of be like the diamond.
yeah, exactly. Yeah, exactly. That's a good way to think of it. Yeah, indeed. Yes. Hi.
I asked a question about what defines a binary search tree, because I missed that step when you were showing
Sure.
like why was
Oh, want to come over here? Yeah. Yeah, come over here. Yeah. You mean the search property, right? Yeah, so that one there, yeah, so that's to say everything in the left, they have the key value strictly smaller than, yeah.
I mean the other example where like you made one.
Oh,
like,
okay.
Yeah, why is this one still a binary search tree?
Okay.
Sorry, because I missed the part like the step right here where.
No problem.
Yeah.
So let's say that's what we have. So if you look at this particular subtree, this will still be a binary search tree because if you look at this is the root, this is a left subtree. You can see every element here strictly less than that. And there's nothing here, so it doesn't violate. And then we go further to look at this particular smaller subtree. That one is still a BST because this one, 69, is strictly smaller than the key of the nodes in all the right subtree. So this is still a BST.
Oh, so it's just the left node has to be smaller than the right node.
Yes, that's correct.
Oh, okay,
That's
so
correct.
then for this one, that's 83.
In that way, you can see 54 indeed is smaller than that. That part is okay. But now if you look at that,
Oh, but this one is.
it's not the case that every node in the right subtree is actually greater than this. It's not, because you can see 82, for example, is not greater than that.
But then if, let's just say this was 84, then...
You mean this one is 84?
Yeah, if that was 84, then it would be a binary search tree.
No, because 76 also is not greater than that.
Okay, so it has to be
Every node in the right
every node
subtree.
below it. But then, for this specific case, then it's... Sorry, I'm just not seeing the sorry, I'm just not understanding the disconnect between it, because by saying that this is still all less than 83.
This one, yeah. So well, if there's any number that's
So
not,
it needs to be
yeah,
greater
if there's any number that's not greater than 83, you find some weakness to prove.
So just
it's not
everything in the left needs to be
smaller than.
less than, and then everything in the right needs to be
That's correct.
greater than?
Greater.
Oh, okay. So then if we had another node here and it was, actually, sorry, on this side, that would probably be nicer. If this was like 84, it'd be fine.
Like greater than,
You mean this one 84?
Oh, sorry, if you just like added an extra node there and you made it like 84, it would be fine? Or if you made it,
This adding here will be okay
Yeah,
because
or-
84 is greater than that.
or if you made it,
Well, maybe, you know what? This is one way to check it, but based on the sorting property.
Yeah.
If you just do, maybe that might be a little bit easier.
Well, yeah, the
Just
sorting
do a in order traversal to see if you get a sorted sequence. In this case, you wouldn't get a sorted sequence, right? Over here.
I
It's
just
not.
prefer not to do that every time. So I just want, so
Yeah.
it's just the right nodes always have to be greater than the left. Essentially. Okay.
Exactly. Every node in the right subtree.
Yeah, I just think I missed that slight detail for the.
That's okay.
Thank
It
you
takes
very much.
take some time. No worries.
sorry, sir, for interrupting. Like for searching a node, like a value, then does it always have to be a BST, or like it can be any tree? Like
If you want to do binary search, then it has to be a binary search tree.
no, like for searching a value, like 28, you said like.
Well, so of course to search, if the tree itself is not a binary search tree, then you have to check both branches.
Yeah.
If it's a binary search tree, then you only need to check
Yeah,
one
but
branch.
we can search any tree.
You can search any tree, of course.
And what was the like? I couldn't understand.
Why don't we talk after the lecture? Okay. All right, guys, we should really resume, please. Yeah, I'll talk to you maybe after class. Okay. All right, guys, let's resume, please. Okay, so before the break, we spoke about this BST node again. Okay, so some of you actually asked me during the break. I think it's a very legitimate question. Here's the principle. Whenever you're given, let's say, a tree, and the question was whether or not it's a binary search tree. So there are two ways to check it. Okay, either I would say the simplest way is just to do an in-order traversal, and then check to see whether or not it's a sorted sequence, like what we said before the break, right? That's one way. The second way is you have to do recursively to say, let's say, given some node over here, is the subtree rooted at this particular node a binary search tree? And in order for that to be a binary search tree, every node on the left should be smaller than, every node on the right should be greater than, right? Not only that, you have to go for every node being the subtree, right? So you got to go kind of recursively. I would say it depends on which one might feel more comfortable, you would just do a combination. But in the exam, you just have to choose one way or the other. Okay? That's what we talked about before the break. And let's now try to see how we can manipulate the binary search tree node. Okay, let's do one example. And this one here, let's see how we can do in order traversal. In your practice test, you actually did some exercise on pre-order traversal, and now we got in order. And of course, what's really left? You should really try that as a remaining exercise yourself. Okay, let's take a look. This will be the method we can define. You can see we simply got another class called BST utilities. We just want to do some in-order traversal. Let's look at the method header. So we have in-order traversal over here. The input is some BST node, which will be the root of some binary tree or binary search tree. We assume that it's going to be binary search tree, let's say. And the output is going to be an array list of BST node. Okay? And of course, in your programming task, you wouldn't be allowed to use any Java API like last time. So I would encourage you guys, after today, you really want to try some exercise over here. I'll put it here. So rather than just array list, what if the output the return type would be, let's say, BST node. What if just, BST node, primitive array. Rather than an array list where every element is a BST node, what about an array where every element is a BST node? And number two, which is more relevant to your programming test, SLL node. And then every element there is going to store BST node. Again, if you're having trouble understanding this kind of nested generics over here, in your assignment number 3 instruction, there were some detailed notes about how to distinguish between them. Okay, you're supposed to grasp it or maybe reach out. There will be some extra exercise you can also try. And of course, how do you do pre-order? And of course, how do you do post-order? They should be rather similar. You just have to change the order of calling the recursion, right? That's what we said last time. But let's try to understand this part here, okay? And we're saying that we are having some result, which will be the array list that we want to return. Ultimately, we just return the result, okay? And then this block over here tells us we only have to bother doing some computation if the node that we are looking at is actually internal. Now, think about what's happening here. If you look at the diagram here, let's say this one. If you want to do in-order traversal of this particular tree, so you don't really have to worry about doing any in-order traversal on the external nodes. They should be just skipped. That's why we got that if conditional there. So you just have to traverse 8 and followed by 17, followed by 21, and etc. You can disregard the external nodes. Okay? That's point number 1 you have to watch out for. And then, let's see what's really here. Well, here should be very, very corresponding to what we learned from last Wednesday. Okay? Let's take a look. Here, you can see, let me just visualize this for you a little bit. Let's say the root, which is the input over here, right? So we have the root. And we already know root is internal. So that means the root has non-null, left and right over here, right? So think about this part over here is the left child. And of course, this part here is going to the left subtree. Okay, left subtree. And similarly, think about this node over here is the right child. And that one there is also going to be another arbitrarily complicated subtree, right subtree. Right? And what do? We're going to say if the root dot get left over here is also internal, if that's not external. In that case, we can now try to do some recursive call on the in-order traversal. And this one here, you can see in-order traversal, which is a recursive call. And then that one there is going to be root dot get left. Right? So you can think about, we just say in order. Okay, think, let me just say do this. So think about this one here. We're doing in order traversal of root dot get left. And that one there is going to give us some array list. Okay, that part there. Okay. And similarly, if you look at this part over here, this part here, we are also making another recursive call. That one there, what are we calling? Root.get right. Right? So think about if we try to make a recursive call over here, we're going to make in order traversal of root dot, let me write a little bit better. Root dot get right. Okay, that one there is also going to give you some array list. So now we got two array lists, one here and one here. And also we got a root. How do we combine them? Right? That's what we did last time. The idea would be you have to take this list first, append root to the end, and then append this also to the end. Okay? I'll write it down here. The in order traversal result would be something like, first of all, you got this list over here. Array list, followed by the root, followed by this array list. So this will be the result. And the way we try to join these three parts together is by using the add/or method. Okay? So think about what we are doing over here. To put everything together is, okay, this part over here, is by using the add/or, add, and also add/or together, right? Ultimately, we can just return this result. That's the code structure. Are we good about this? Okay, let me recap. We know that in order to do in-order traversal, given the root, you have to do in-order traversal recursively on the left subtree, followed by the root, and do the in-order traversal on the right subtree. That's exactly what we're doing here. In-order traversal on the left subtree, in-order traversal on the right subtree. In between, we just do the root. But programmatically, how do we join the results together? Because I know each recursive call is going to give me back an array list. So this part here is going to give me some array list. This part here is also going to give me some array list. And I simply just use the add/or method in the array list to add everything appending to the end. Okay? Hopefully not too bad. And you can do, hopefully within 20 seconds, to change this into pre-order and also post-order. Do you guys know how? If I say this is block number 1, this is block number 2, this is block number 3, how do I change it to be pre-order, for example? Yes? Yeah, you can switch block number 2, put it here, right? That guarantees you're going to visit the root and then left subtree and right subtree. And you guys can think about the post order. Okay, I want to be more precise here. Think about this is, okay, block number 1. And think about this one over here is block number 2. And think about this one over here is block number 3. Now, if I change the problem into pre-order traversal, in that case, you're going to do B2 followed by B1 followed by B3. Okay? And think about post-order as well. And write some test cases yourself. That will definitely help your understanding. Okay? All right, any question? That's about the method. We haven't got a tree in the first place just yet. Let's see how we can build a tree and call this method. That'll make it complete. And all the source code, I'm going to make it available to you. You can also give it a try. Okay, this will be how we build a tree. Looks a lot, but it's not too bad. Looks a lot. Let's take a look. And for this one here, let me look at my notes. I'll draw very carefully to show to you. Overall, we want to build a tree that looks like this, conceptually. We want to build a tree that has only 3 nodes. 1, 2, and 3 over here. And then we want to have 28 Allen. And also we want to have 21 Mark. And finally, we want to have 35 Tom. And what I'm going to highlight in pink, so these are the key values, right? And Alan, Mark, and Tom, they are the data value, right? Remember we said an entry consists of two parts, right? And we want to somehow connect them in this way, okay? Left child and right child. Is this a binary search tree? It is, because 21, 28, and 35 is sorted. I just did it in order traversal to double check. Alternatively, left subtree over here, all the key value 21 is smaller than this. Right subtree, all the key value 35 is also greater than this. Right? That's the second way to do it. And to be even more precise, we want to also have external nodes. That's the part I want to show you as well. So conceptually, this is the tree that we want to build, conceptually. And after we have built this tree, we want to do an in-order traversal over here, starting from this node. That one there is going to give us 28, followed by 28, sorry, 21, followed by 28, followed by 35. And that's what you will see later. And I haven't shown you how to build a tree just yet, but I want to highlight other things. If you look at 21, followed by 28, followed by 35, this will be the sorting property. Right? Which we spoke about before the break. And the mystery now is to see how we can build the tree. Let's look at that quickly. Okay, let's say this part here. How many BST nodes do we have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? 3 internal and 1, 2, 3, 4. 4 external. Okay, let's do that. So what we're going to do is N28, N29, N28, N21, and N35. Let's do that. And I have some skeleton here that can help me. So what I want to do is, let's say 1 here. Okay, and then 1 here. And also 1 over here. Right? 3 objects. So N28 is going to be this one here. And N21 is going to be this node here. N35 is going to be this node over here. All right, the reference. Let's look at the contents. 28 will be the key. And Alan will be the value. Okay, we can think about it's going to be Alan. And 21 and Mark. 21 and then Mark. And 35 and Tom. 35 and then Tom. Right, setting just the key and values. And of course, when you do the searching or checking the search property, only look at the key value. Right? Let me just highlight it again. Key, key, and key. Okay? And we also have 1, 2, 3, 4. 4 external nodes. Right? For them, let me just use the square box, so that's kind of easier to draw. Okay? So I'm just going to put 1 here, 1 here, 1 here, and 1 here. Okay, so they will just be external nodes. And as I mentioned before, we're just going to call the empty argument constructor over here to create external node 1, 2, 3, and 4. Okay, so it's going to be external node number 1, external node number 2, external node number 3, external node number 4 is this. Right? So far we got 1, 2, 3 internal nodes, 1, 2, 3, 4 external nodes. Right? 7 objects that we have created. They have not been connected just yet, okay? Which I'm going to do. And that'll be the remaining part. If you look at this part here, that's how we're going to connect them together. And they're not too bad. So for example, N28, which is this node over here. Set the left to be N21. N21 is over here, right? I want to set this node here to be its left. So that's what I do. Okay? Symmetrically, N21 should have N28 as the parents. So that means its parents should really point back over here. So far I have set 2 references. Let me just get rid of this. Are we okay with this? So here you can see N28 does set left to be N21. And also N21 does set parents to be N28. Right, symmetric. And we're going to do all these together. Okay, let me just draw that. So what we're going to get is, so N28 right is going to be this node. Symmetrically, its parents is going to be this. Right, so that's what we have over here. And then we have to make sure external node number 1, number 2, their parents is simply N21. So that means left should be here, right should be here, the parents should be here, and the parent should be here. Left here, right here, the parent point back, and the parent point back. So these are the pointers we have to set accordingly. Okay? Some important question you want to ask yourself, since we are programming in OOP, something about aliasing. Okay? And let's put it down. Just one example. Let's say aliasing. Let's say I want to talk about this particular node. How many ways are there for me to reference this particular node? One would be I can give to you N21. Are there any other ways to reference this node? Thank you. That's one. N28 get left. Thank you. Would that be it? Ferrets. Yeah, absolutely. External node 1, the get parents, and then, yeah, that's it. Very good. Okay, let me give you one more. Okay, you can also try. It could be N28 dot get left, and then the get right, get parents. That can also work, right? Okay. So this is another one. N28 the get left, the get right, the get parents. Okay, that'll be another one. And I'm pretty sure there might be more. So that's kind of the aliasing observation you have to make by yourself, right? So just for this particular node, there might be multiple different ways to refer to it. You have to be careful about aliasing, right? That's what you guys learned in 2030. Given this particular tree structure, you might be wondering, if you're given this some tracing question in the exam, for example, should you draw the tree in this way or this way? I would say completely up to you. If you're feeling comfortable enough, just by looking at this, you will know how the various attributes should be set up. That's okay. By all means, you should really go with this one. But if you're feeling less confident about seeing how the attributes like parents, left and right, and value key, etc. have been set, you may want to try with this one. It wouldn't take you much longer. Okay, I'll leave the decision to you. What's really left is over here. If you look at this line over here, so what we're doing is we're calling the in-order traversal method, which we define in the earlier page, right? We talk about it, okay? And what's really passed as input is N28, which means we're going to do an in-order traversal on the subtree rooted at this particular node, which is going to cover 1, 2, and 3. And we are not going to include external nodes. If you try to trace the algorithm, you will see that, okay? And the final thing to remark will be, if you look at this particular in order list, you try to get to index 0, index 1, index 2, right? If you look at that, index 0, index 1, index 2, and you look at the key values. In that way, you're going to see 21 followed by 28 followed by 35. That is sorted, sorting property. Okay? Okay, any question about this? We good? Okay. Let's see. Go over, sorry, which part? The last part, okay. So if you look at that, we're calling it in order traversal method. And the input here is N28, which means we want to do in order traversal on the tree rooted at this particular node. And that one there is going to involve 1, 2, and 3 internal nodes. So that's why the resulting sequence is going to consist of the 3 key values, which will be 21, 28, 35. Right? That's sorted.
And this just goes back to our original surface code that we had.
Yeah, exactly. So what we said before the break was the theory. The theory was if you try to do in order traversal on your binary search tree, you're going to get a sorted sequence. And now we actually put it in Java and we prove that by this particular example. You're really going to get a sorted sequence if you implement it, the in order traversal properly. Okay? Okay, we got about 2 minutes or so. Let's see if we can do any more. Okay. Okay, I think now we should be good. Let me just give you 1 minute of a look ahead about what you guys may want to do before Wednesday. Of course, now your priority should be 3 things, guys. Number 1, prepare for your programming test 3. That's for sure. That one's more urgent. Number 2, I would say we covered quite a bit of material so far in the course. You may just want to start going over the materials already for your exam. It's going to be cumulative. Okay, so that one they really want to plan for that. Even though the exam is about close to a month away, but you wouldn't have that much time given that you got other things to do. Number 3, for Wednesday, I think we have covered the trickiest part for the binary search tree, which is about how to build a tree and how to understand the search and sorting properties. On Wednesday, I definitely want to finish 3 things to conclude this topic. Number 1, how do we do searching on a binary search tree? And that one there, not just to present to you the algorithm, we want to draw some connection to how do you compare doing a binary search tree search compared with some sorted array binary search, which you learned in the makeup lecture. We want to draw some connection to it. After that, we'll talk about running time. And then we'll talk about how you can do insertion and deletion in the binary search tree. In that case, you have to be careful about what you do. And then hopefully we have time to move on to balanced binary search tree on Wednesday. All right? Okay, that's it. Thank you so much. If you have any trouble with the course, reach out.